This this video is on hardware description language. So basically there are two standard HDLs that are supported by IEEE. One is VHDL, another one is Verilog HDL. VHDL is very high speed integrated circuits hardware description language, and sometimes it is referred to as VHS IC HDL. This was developed from an initiative by US Department of Defense. And second type of standard is Verilog HDL. It is developed by Cadence Data Systems and later transferred to the consortium called Open Verilog International. So this is easy to understand, but this is more reliable. And if you consider the Verilog HDL has a syntax that describes precisely the legal constructs that can be used in the language. It uses almost 100 keywords predefined and lowercase identifiers that define the language constructs. Example of keywords include module, in module, input, output, wire, and, or, not, and so on. Any text between two slashes and at the end of the line is interpreted as comment. Blank spaces are ignored and names are case sensitive. If you consider the Verilog module, a module is a building block in Verilog. It is declared by the keyword module and is always terminated by the keyword end module. Each statement is terminated with a semicolon, but there is no semicolon after end module. Let us say now we are going to design or write a Verilog program for this logic circuit. See, A and B are performing with AND gate, and the output of this AND gate is given to the OR gate, and C is given to the inverter. Okay, and that C which is giving a C bar, and that is given to gate G3, and you are getting your X. Now your X is A and B. Okay, plus C bar, is it? Just performing R with C bar. This is your X's. Y is, it is C bar, is it? So now we are going to write the Verilog code for this combinational or boolean expression, that is for the logic diagram. See, the module name is module. Module name, it can be of any name. The inputs are A, B, C, and then X, Y. Outputs are X and Y. Hence, and end with a semicolon, is it? And then the inputs A, B, C are declared and end with semicolon, and output are X and Y. The intermediate, see, this is a wire. Is it? The output of AND gate is connected to input of OR gate. Hence, this is declared as wire here. Hence, it is wire E. Okay, now A and B are the inputs to the AND gate, and E is your output, AND is your keyword, and G1 is your structural instantiation. So this is AND G1 E comma A comma B, is it? E is your output, A and B are your inputs. And similarly, the NOT is NOT keyword is called, and this is a structural instantiation for your NOT. Y is your output, C is your input. That in which Y is equal to C bar here. Okay. Now this is given to the OR gate. See, this is your Y output, is it? And now we got our output Y, which is equal to a C bar. Now our output Y is equal to C bar, is it? And here C or G3. OR gate is your keyword, and G3 is your gate structural instantiation for OR, in which E and Y are your inputs. See here, E and then Y, which is equal to C bar, is given as an input to the OR gate, and these two are performing OR operation, and then that is stored in the result X. Your X is your output, is it? So now you are end your module. This is how you need to write your basic Verilog module. And next, you can give the delays, gate delays in your Verilog. So that can be done by, see, with the help of the, in Verilog, the delay is specified in terms of time units and the symbol hash. The association of your time unit with physical time is made using timescale compiler derivative. Okay, see how it can be given. The compiler derivative starts with the backcode, which is symbol. See, this is your back single quotation, is it, with the backcode time scale, in which you can give any either you can give nanoseconds or picoseconds. Okay, the first number specifies the unit of measurement for time delays. The second number specifies the precision for which the delays are rounded off. In this case, 2.1 nanoseconds. In any way you can define. See here, I am defining with the delay. See, module circuit with delay. The same circuit is utilized here, but we are adding the delay. See here, I am using and hash 30, which means at 30 nanoseconds delay. Is it at 30 nanoseconds delay? Okay. And similarly for OR, I am giving 20 nanoseconds. Similarly for NOT, I am giving 10 nanoseconds. With delay, I am working with the Verilog modules. Okay. Next is the test bench. So in order to simulate a circuit with HDL, it is necessary to apply inputs to the circuit for the simulator to generate an output response. And HDL description provides the stimulus to a design called a test bench. See, we are going to give the inputs to work whether the circuit is working proper, to check whether the circuit is working properly. So that we can write with the help of your HDL description. The initial statement specifies the inputs between the keyword begin and end. Initially ABC is equal to 0, 0, 0 is given, and the system task is end with hash finish, that is dollar symbol finish. Okay, see here, this is your Verilog module and this is the stimulus for your simple circuit. This is actually a test bench circuit. This is actually a test bench circuit in which you are giving your input to check this circuit or to simulate this circuit. Okay, see here, module stim circuit. You can give any name. Is it module name? In which, see here, the inputs here are written with the registers A, B, C, and outputs are written with wire. See here, the outputs here are X and Y, you know about it. And in the test bench, it should be written as wire X, Y. Okay, and this circuit should be called for starting your simulation. That is why a module name is called circuit underscore with underscore delay. This is your module name. With module instantiation name. Any name can be given. It can be C1 also, or it can be any name as D1. Okay, or it can be D. Any variable can be given, but it should not be A because A is already declared here. Okay, so a module instantiation is given. See, within that you have to call ABC, X and ABC or your inputs, X and Y or your inputs, and then your initial. You are starting with initial, and then you are begin your stimulus. Okay, in which you are giving A equal to 1 bit 0 and B equal to 1 bit 0 and C equal to 1 bit 0. Now you are giving the input 0, 0, 0 to this circuit, and after 100 nanoseconds you are giving A is equal to 1 bit 1, B is equal to 1 bit 1 and C equal to 1 bit 1. So that is why it is 1, 1, 1. 3 bits are given, and then hash 0, hash 100, which is a time delay. And after that also you can give one more stimulus input. See, I can give also 1 bit 0 semicolon B is equal to 1 bit 1 semicolon C equal to 1 bit 1, which means that 0, 1, 1 can also be given. Okay, and then you can give hash 100 and then you finish it. And then finally, as you are beginning here, you end it here, and as you are beginning your module here, you perform an end module here. This is how you need to write your test bench for your given circuit. Okay, this we can say it as a stimulus for a simple circuit. Okay, see, this is the circuit that we have designed, and this is the circuit that we have used for stimulation, which helps to give inputs to this circuit that we have designed.